Okay, we are on section 10.2 looking at comparing to populations or groups. This time we're looking at comparing to means. We had just finished the section on comparing to proportions. You'll find a lot is the same, only our calculations for means and proportions are slightly different. Otherwise, all of the processes are the same. So we're going to look at shape, center, and spread of the sampling distribution for the difference of two means, determine whether conditions are met, construct and interpret a confidence interval, perform a significance test, and determine whether it's appropriate to use the two-sample t procedure versus the paired t procedure, which we talked about in section 9.3. So what if we want to compare the mean of two different populations? So similarly to how we did this with the proportions, we're going to have to label each parameter, statistic, and sample so we know which one is which when we are organizing ourselves in our work. So for population 1, you're going to have mu1 for the parameter, x bar 1 for the statistic, and n1 for sample size. Same thing with 2 all the way across, making sure that we label appropriately. So if we're looking at, as an example, we have the heights of 10-year-old girls following a normal distribution, where the mean is 56.4, standard deviation is 2.7, and the height of 10-year-old boys follows a normal distribution where the mean is 55.7 and the standard deviation is 3.8. Suppose we take simple random samples of 12 girls and 8 boys and measure their height. What can we say about the difference of x bar for females minus x bar for males in the average height of the sample of girls and the sample of boys? So if we look at, unfortunately this one did not turn out like the one, it turned out pretty okay for the proportions. It did not turn out for this one that got kind of cut off, so I'll write down the sample data for us. So our shape here is obviously approximately normal. The center, the mean like we had mentioned before, is 56.4 inches, and the standard deviation is 0.8. The sampling distribution, remember, because we have to divide the standard deviation they gave us by the square root of the sample size. The mean for boys is 55.7, and standard deviation is 1.35. So unfortunately our shape got cut off, the picture did, but as long as we know that these two are approximately normal in shape, then we know that the difference is also going to be approximately normal in shape. The center, I apologize for it being cut off. The center, the mean of that sampling distribution is at 0.67. And the standard deviation is at 1.56. So how did we get those things? We just have to remember how to combine variables from chapter 6. Remember that when we're finding the difference of means, we just subtract them, and then find the difference in standard deviations. We have to treat them as their variances, and you have to add the variances. So our shape, as long as population is normal, then sampling distribution is normal. And that's of the differences. If we don't know, remember that if we don't know about the population shape, then we have to have at least 30 for both of our sample sizes. We'll cover that again in a little bit. Center, the mean of the sampling distribution is mu1 minus mu2. And the standard deviation is the square root of the variances added together. As long as the 10% condition holds. Okay, so here's what this looks like. In the middle, this is the sampling distribution for x bar 1 minus x bar 2. The mean is mu1 minus mu2, and the standard deviation is what we just stated there. The variance is added together and the square root of that. Okay, so let's look at the sampling distribution, shape, center, and spread of this scenario. A fast food restaurant uses an automated filling machine to pour its soft drinks. The machine has different settings for small, medium, and large drink cups. According to the machine's manufacturer, when the large setting is chosen, the amount of liquid is normal, mean is 27, standard deviation is 0.8. When the medium setting is chosen, then the amount of liquid M dispensed is a mean of 17 ounces, standard deviation of 0.5. To test the manufacturer's claim, the restaurant manager measures the amount of liquid in each of the 20 cups filled with the large setting, 25 cups filled with the medium setting. Let x bar L minus x bar M be the difference in the sample mean amount of liquid under the two settings. What is the shape? So the sampling distribution of x bar L minus x bar M is normal because both populations are normal. Which was stated in the question. The mean of x bar L minus x bar M is the mean for large minus the mean for medium, 10. Standard deviation for x bar L minus x bar M is the two variances added together in a square root. So we have the variance, or the standard deviation of the large was 0.8. So we have to square that to make it the variance and divide by our sample size. Same thing, we have the standard deviation for medium is 0.5, so we square that and divide by its sample size. And then we add them together, and both we have to take the square root of the whole thing to get back to standard deviation, which is 0.205 ounces. Okay. So we have to calculate this two-sample t-test statistic. So this is going to be our, if we know the population standard deviation, obviously that's going to be our standard deviation of the sampling distribution for the differences, but a lot of times we don't have that. So we have to go next page here. We're going to use, again, what's called standard error instead of standard deviation because we don't have the population variance. So we use S instead of sigma. If I'm going to calculate the t-test statistic, we do the difference of the x bars on top minus the difference of the means over the standard error. And we are going to have, remember with the t-test statistic, we care about degrees of freedom. Now this time we have two samples to worry about. So how do we know which degrees of freedom to use? There's going to be two. So what we're going to use is always the smaller of the two. And -1 for each sample size, and then whichever one is smaller is going to be the degrees of freedom that we use. So looking at our conditions, as this should start looking very familiar, they either have to be two independent random samples or two groups of a randomized experiment. 10% condition only when we're sampling without replacement. Both of our samples have to be less than 1/10 of the populations that they go with. And then we either have to know the populations are normal, our sample sizes have to be large, or we have to graph them both to see that we don't have strong skewness or outliers in our populations. So the confidence interval is what we're looking at next here. To find the confidence interval for mu1 minus mu2, we take the difference of the sample means out front. We use T star and then our standard deviation, which was S1 squared over N1 plus S2 squared over N2. And we use degrees of freedom, whichever one is smaller. Okay, the Wade Tract Preserve in Georgia is an old-growth forest of longleaf pines that has survived in a relatively undisturbed state for hundreds of years. One question of interest to foresters who study the area is how do the sizes of longleaf pine trees in the northern and southern halves of the forest compare? To find out, researchers took random samples of 30 from each half and measured the diameter of the breast height in centimeters. Below is comparative summary statistics. So they did that for us, which is very nice. It's based on the box plots created from the data above and numerical summaries. Write a few sentences comparing the sizes of longleaf pine trees in the two halves of the forest. So why don't we just do a quick sketch of what these box plots would look like. We'll do side by side. The smallest for either would be 2, so why don't we start at 0, and the biggest for either is 59, so let's go from 0 to 60. Because I don't really need this guy over here. So on top we'll do the north in the black color. Minimum at 2, Q1, median, Q3, max. Oops. Okay, that's what that one looks like. We'll do the south in red. Our minimum is 2.7. Q1 is 25.5. Median is 37.5. 45 and 53. This dot should be down lower. There we go. Okay. So if we're looking at the two distributions here, we'll underneath, I'll put our sentences comparing, a couple sentences. If we're looking at the shapes, it looks like the north DBH heights is skewed right, and the south is skewed left. Trees in the south have larger diameter mean and median. The trees in the south have larger mean and median than those of the north. So those are our comparative words. North has more variability, has a larger IQR and a larger spread overall. Let's go back up and look at standard deviation as well. Yep. IQR, standard deviation, and range. No outliers in either. So we covered SOCs in those few sentences to make sure that we described them properly. With that data, let's construct a 90% confidence interval for the difference in the mean DBH of longleaf pines in the northern and southern halves. So we are looking at we need means, standard deviations, and sample sizes for the confidence interval. So we do if we're going to do north and southern halves, then we're going to do, let's do south minus north, because I can tell south is bigger. This way we'd get a positive confidence interval. You could absolutely subtract the other way, not an issue at all. 90% confidence interval, our T star. If we look at the table B, because our DF is 29, since both of our sample sizes are the same, our T star is going to be 1.699 from that table. And then we take our standard deviation, square it, divide by the sample size, and the other. Which is going to give us an interval of 3.83 to 17.83. Now we need to interpret. We are 90% confident that the true mean difference between the south and north, since I did south minus north, DBH height, is between 3.83 and 17.83. So now let's look at what we need to do for a significance test for mu1 minus mu2. Our null is always going to be mu1 minus mu2 equals some hypothesized value. Most of the time it's going to be mu1 is equal to mu2. So remember, I'm going to rewrite these alternative hypotheses as well as mu1 is greater than mu2, mu1 is less than mu2, or mu1 is not equal to mu2, just for simplicity's sake, but you can certainly use them with the zeros as they have indicated there. Okay, so we have, as always, our test statistic is statistic minus parameter over standard deviation of statistics. So we have to, in our context here, our statistic is x bar 1 minus x bar 2. Our parameter is mu1 minus mu2, which we should have 0, so that is not super important. And then our standard deviation is s1 squared over n1 plus s2 squared over n2. Notice, unlike the proportions, we don't have to have a pooled standard deviation, where they had a pooled proportion that you use in the standard deviation. Here for means you don't have to do that. And then you choose the smaller of the two degrees of freedom to find your p-value. And you'll have a range of p-value just like you did with a one sample t-test. So again, here that is all of the things that we need, knowing that if it's a greater than, that your p-value is going to be on the right. If it's less than, your p-value is going to be on the left. If it's not equal to, your p-value is going to be both tails of that t-curve. Okay, so let's go through one of these tests here. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed the relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation, so researchers therefore designed a randomized experiment to compare. There were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to 2 groups. 10 of them got the calcium supplement, while the control received a placebo pill that looked the same. The experiment was double-blind. The response variable was a decrease in systolic blood pressure for a subject after 12 weeks. An increase would be a negative number. So you want that to be positive. You don't want your blood pressure to have a negative number. That would be an increase in your blood pressure. So let's start with our 4 steps state, where we state our hypotheses. HO is that our 2 mu's are equal. And if we claim this is 1 and this is 2, then we would want the top number for population 1 to be greater than population 2, since we would want positive changes in blood pressure as opposed to negative changes. Okay, so then we state our alpha value and what mu1 and mu2 stand for. mu1 and mu2 are the true decreases in systolic blood pressure for black men who took calcium and placebo, respectively. Plan. We have to check all of our conditions here. So we are doing a 2-sample t-test for the difference of means. Let's check our conditions. First one being random. It's a randomized experiment. Randomized to treatment. 10% don't need for experiments. Large sample. Do we have a large enough sample size here? No, these are both small. We have 11 and 10. It does not say anything about the population shape, so we are actually going to have to go into our calculator and put both of these in and look at their box plots. So I'm going to put my group 1 into my list 1 on the calculator, group 2 into list 2, and then I'm going to do side-by-side box plots. I will pause and get that all typed in. So I did go ahead and put all the data in, and I put them in as 2 box plots. I don't see any outliers. They would be indicated with asterisks on either of those box plots. There is some skewness to each, but nothing too severe. So I'd say we're okay to do our T procedures. Some skewness, but no outliers. Okay, so now we're going to the do step, which is the t-test statistic. So we're going to do the x bar 1 minus x bar 2. So I don't have a lot of that written down. So before I actually calculate it, why don't we write these things down? All of the things that we're going to need, and then have our calculator help us out with those. So we're going to need sample size. We have that, I should say. We need the standard deviation for each. That should do it. So let's go back to our calculator. Calculate one variable statistics for list 1. X bar 1 is 5, X and S is 8.743. Do the same thing with the X bar 2. One variable statistics for list 2. Our X bar is negative 0.273. And our standard deviation is 5.901. Sample size here was 10. Sample size here was 11. Now with all of that, we should be able to calculate our t-test statistic. X bar 1 minus X bar 2 minus 0, so I don't have to write that, divided by our standard deviation, S1 squared over N1 plus S2 squared over N2. This should say N2. And our t-test statistic is 1.604. With that, I'm going to use my degrees of freedom as one smaller than my smallest sample size, so it's going to be 9, and then with that I'm going to find a range for my p-value. It's going to be between 0.05 and 0.1. With a large p-value such as this, we are going to conclude that there is no difference. So let's write that officially. Since p is greater than alpha, we fail to reject Ho. We do not have evidence that the true mean decrease in systolic blood pressure is higher for men who take calcium. Versus placebo. Okay, so we did letter A here. Does the data provide convincing evidence? We did that. Let's look at letter B, interpret the p-value in context of the question. So we had our p-value, as a reminder here, was between 0.05 and 0.1. So assuming the means are equal, there is a chance between 0.05 and 0.1 of getting a difference in mean blood pressure reduction for the two groups. And we did calcium minus placebo. Of 5.273 or greater, just by chance. And in this case, our chance was from the random assignment. Okay, so now we're looking at how to use two-sample T procedures wisely. When we're planning a two-sample study, choose equal sizes if possible. We don't do anything pooled. Remember I mentioned that for proportions we do pool the proportions, but we do not pool anything for two-sample T's. We are safe using two-sample T procedures comparing means for randomized experiment, which we just did. Do not use two-sample T procedures on paired data, which I think is the biggest issue, is that we need to be able to tell the difference between paired data and two-sample data. Beware of making inference in the absence of randomization. The results may not be generalized for the larger population of interest. That's why we check random, right? That's one of the things we need to check every time. So here we need to look at what the difference is between the paired T procedures that we just talked about today, or that we talked about in chapter 9, and versus the two-sample T procedures that we just talked about today. So let's figure out which one's correct and why. To test the wear characteristics on two tire brands A and B, one brand A tire is mounted to one side of each car in the rear, while the brand B is mounted on the other side. the coin gets flipped, and then that determines which side the tire goes, the brand that goes on each. So because these are kind of paired, right? Like there's the wheels on each side of the car, this is a matched pairs experiment. I guess I should use the same color I underlined with up there so we're not confusing people. So this is matched pairs. Since 2 treatments are randomly assigned to each pair of wheels. Which again then would, I guess then would make B the 2 sample, but let's read into it to make sure. Can listening to music while working increase productivity? 20 factory workers agree to take part in a study to investigate this question. Researchers randomly assign 10 workers to do a repetitive task while listening to music, and the other 10 do it in silence. So because these two are completely different, it's not like it's a before and after of the same person. This is the 2 sample T. Two distinct groups of workers. In the randomized experiment. Okay. And that was it. We finished learning about 2 means, finding the sampling distribution, shape, center, and spread, how to do a confidence interval, and how to perform a significance test for the 2 means.